Hi everyone, I'm Laurence Moroney, the lead AI advocate here at Google, and thank you so much for tuning in. Since the TFDS in March, the last time our global community came together virtually, a lot has happened. There's been a global pandemic. A resurfaced fight for racial justice is happening all around the world. Many of us are experiencing changing personal circumstances and a different way of working. In times of uncertainty, it's core to who we are to turn to technology, like machine learning, to help. We found comfort in knowing that we're part of an important infrastructure for the world that has the ability to help others. For example, within Google during these times, we've seen how TensorFlow played a timely role in supporting Google Meet, and that's our video conferencing software. You can see it being used as an education platform in the bottom middle photo. TensorFlow helps the software adapt to changing bandwidth, and it enhances picture quality. Since making Meet's advanced features free for all of G Suite and G Suite for Education users in March, we've seen daily usage grow by 30x, and Meet has been hosting 3 billion minutes of video meetings daily. And there's a blog post with more details here. This is just one example of how TensorFlow is helping us adapt and support new forms of communication and collaboration. For TensorFlow itself, we're seeing unprecedented scale and growth. TensorFlow crossed over 100 million downloads, with over 10 million in 1 month this summer alone. We've had 45 million tutorial and guide views. We've had more than 8 million reads of articles on the TensorFlow blog, and more than 8.1 million views on the YouTube channel. And between Coursera and Udacity and our other MOOCs, we crossed over 500,000 learners. This is a testament to the community, so we want to say thank you so much for continuing to support TensorFlow. We have some exciting new updates, but first I'd like to recap what we launched the last time we got together at the TensorFlow Dev Summit. We hosted our 3rd annual Dev Summit in March, and we've announced a lot of exciting updates. For example, we released TensorFlow 2.2, which builds off of the momentum of 2.0, but this release focused on speed and performance, making sure that the rest of the ecosystem was not only compatible with the latest version, but stable in the core library. We also announced new updates for the entire TensorFlow ecosystem. To better enable researchers to get results faster, we announced the TensorFlow Profiler in TensorBoard, and this provides in-depth monitoring of model performance. We also introduced fairness indicators, which can easily compute common classification fairness metrics on your data within TensorFlow Extended and TensorBoard. We also updated and introduced new add-ons and extensions. Most libraries now support 2.x, including TF Probability, TF Agents, and experimental new libraries like TF Quantum, and these let researchers explore and build hybrid quantum classical machine learning. For production users, we also had some exciting updates. In TensorFlow Lite, we introduced best-in-class performance for accelerators. We also significantly reduced latency without requiring any model changes. We've added Android Studio integration so that you can automatically generate the Java or Kotlin classes for your TF Lite model with just a few clicks. We've rebuilt the TF Lite converter from the ground up to provide support for more models, more intuitive error messages when conversions fail, and of course support for control flow operations. For JavaScript developers, we announced new models in TensorFlow.js that are now available for quick integration like Face Mesh and Mobile BERT. We're also excited to feature Hugging Face's NPM package for question answering directly in Node.js. And of course, with WebAssembly backend, you should see performance improvements on CPUs. We shared how using TensorFlow in production got even easier with an exciting launch, Google Cloud AI Platform Pipelines. We partnered with Google Cloud to make it easy to build end-to-end production pipelines using Kubeflow and TensorFlow Extended, all hosted by Google Cloud. But we didn't stop there though. We released version 2.3 in July. The focus on this release was to make it easier to load and pre-process data and to solve input pipeline bottlenecks. And this is done with 2 new APIs in tf.data. The Service API, which improves training speeds by distributing data loading and pre-processing off to a cluster that you'll run alongside your training job. And then there's the Snapshot API, which helps you save and reuse your pre-processing outputs to help improve data pipeline efficiency and overall performance. There are also new features in TF Profiler which will allow you to visualize your model's memory usage over time and trace Python function calls in your model, giving you the ability to spot performance bottlenecks. All of these updates are underscored by the updates that we've been making to the TensorFlow ecosystem. I'd like to touch upon a few exciting updates in each of these areas. First, let's start with talking about the TensorFlow ecosystem for research. The TensorFlow ecosystem has always had a host of add-ons and extensions that are specific to researcher needs. We're constantly looking to keep them updated and easy to use, so we're releasing new updates to popular extensions like TF Ranking, TF Text, Neural Structured Learning, and TF Coder. We understand that ML is often a collaborative experience, so we built tensorboard.dev to enable anyone to easily upload their TensorBoard logs and then get a permalink that can be shared in blog posts, papers, and on social media. Since its launch last year, we've added more of TensorBoard's dashboards, the ability to download metrics data as pandas data frames, and we've added experiment data like title and description and more. We're still at an early stage, but we're excited to see how researchers are using tensorboard.dev, like showing the 550 curves that didn't fit in a paper, or provide access to the raw metrics so that others can reproduce the charts in your paper and explore them even further. But TensorFlow has never just been about pushing the state-of-the-art of machine learning. A model is only as good as its impact in the real world. And this is one of TensorFlow's core strengths. It has helped AI scale to billions of users. So today I'd like to share a few details about what to expect in the upcoming TensorFlow 2.4 release and how we're improving the core experience to help you get your model into production faster. One major focus in this release is on distributed training. It will make multi-worker synchronous training with mirrored strategy more robust against deadlocks. And there'll also be experimental support for parameter server training in tf.Keras. Plus, of course, there's more fixes and improved documentation for better usability. TensorFlow 2.4 will also add support for CUDA 11, allowing support for NVIDIA's latest GPUs. And lastly, there's the tf.experimental.numpy, which will add some support for accelerating some NumPy ops using TensorFlow's runtime, as well as allowing you to use TensorFlow APIs in your NumPy code. TensorFlow Recommenders, TFRS, is an open-source TensorFlow package that makes building, evaluating, and serving sophisticated recommender models easy. Built with TensorFlow 2.x, TFRS makes it possible for you to build and evaluate flexible candidate nomination models, freely incorporate item, user, and context information into recommendation models, train multitask models that jointly optimize multiple recommendation objectives, and efficiently serve the resulting models using TensorFlow Serving. Ease of use is a driving principle for TensorFlow Recommenders, and building a simple recommender system can just take a couple of lines of code. Here, we build a model for recommending movies based on the famous Movie Lens dataset of movie ratings. The model has three components: a user model describing the architecture for representing users, and here you can see it's a simple embedding layer. A candidate model describing the movie representations. Again, here it is as a simple embedding layer. However, extending this to use arbitrary features like text and images is trivial. You'll simply replace it with a more fully fleshed Keras model. Finally, to train the model, we need to define its objective and evaluation metrics, and here we use the retrieval objective. This model will optimize the user and movie representations to retrieve the best movies for a given user. A good model will retrieve the movie the user watched ahead of all other movies, and this is what's measured by the top K metric here. And that's it for the model definition. We can fit, evaluate, and serve it exactly like any other Keras model. If you're interested in more details on how to extend this model to incorporate things like user and item features or multiple objectives, you can check out the Recommenders tutorials at tensorflow.org/recommenders. But for AI to have impact, it needs to be where your users are, which means getting your models onto a device. The new TensorFlow-like task library provides simple model interfaces for popular machine learning tasks. Newer reference apps including on-device recommendation, and even faster mobile inference with OpenCL and XNNPack. It has improved support in the TensorFlow Lite converter for converting TensorFlow RNN operations, including the LSTM, to fused RNN operations in TensorFlow Lite. And these updates are just a few ways we're continuing to improve the developer experience for TensorFlow. But training and deploying a model in TensorFlow is only part of building an AI application. We also want to make sure that you have the tools to make it work for everyone. And that's why earlier this year, we talked about how the TensorFlow ecosystem is committed to the responsible development of AI. Responsible AI is a set of principles and practices that help guide developers in building AI for everyone. It touches upon areas like fairness, interpretability, privacy, and security, while making sure we keep these in mind when we build AI systems. A typical ML workflow will have several stages, and we think responsible AI can be incorporated into each and every one of them. So to do this, you can ask key questions to ensure that your AI system is inclusive and secure. For example, asking, "Who's my system for?" or "Are there any privacy considerations when collecting my data?" are important, because fairness and privacy concerns may be experienced differently in different applications. So tackling these issues is not a one-size-fits-all task. There are several tools and resources to help. For example, TF Privacy's new functionality allows you to assess your model's privacy. Training with privacy is not always possible. The new functionality allows you to measure a model's privacy without having to retrain it. Another tool example is the Model Card Toolkit, which can automate transparency reporting for models. Model cards are a framework for sharing the essential facts of a machine learning model in a structured and accessible way. Building a model card is time-intensive and requires specific expertise. The Model Card Toolkit facilitates this process by auto-generating key model card components using existing pipeline artifacts and displays them in a standardized UI. To help make things easier, we launched the Responsible AI with TensorFlow Toolkit in June. And this toolkit packages all of the responsible AI principles, tools, and resources from the TF ecosystem into a single destination on TensorFlow.org. I want to end on talking about the most important part of what we're building, and that's the machine learning community. So I want to begin by thanking all of you, your feedback, your contributions, and what you build. That's what makes all of this possible. To support these product updates and make TensorFlow more accessible for everyone, we're excited to give you an update on translation. Through a new partnership with Git Localize, we've improved the current Process Contribute experience for community translators by adding Jupyter Notebook support to our tooling. Now it's easier than ever for the community to contribute translations for our runnable documentation. Currently, 13 languages have community-contributed docs: Arabic, Greek, Spanish, French, Indonesian, Italian, Japanese, Korean, Portuguese, Russian, Turkish, Vietnamese, and simplified Chinese. And we're also supplementing the number of translations. We completed the translation of our guides, tutorials, and other documentation into Japanese, Korean, and simplified Chinese, with more to follow. We hope this improves the product experience for our global practitioners. Beyond product updates, at the heart of what we do is bring people together from all around the world to solve AI and ML challenges. These event photos might look a little different, but they make us more proud than ever. It's been great to see what our TensorFlow user groups have been up to, from ML challenges to show and tells and to content viewing parties. As we wrap up the year, we want to share how you can get involved in these events and community groups. One great way to connect is to join a TensorFlow user group. These grassroots communities started organically, and we now have 73 of them globally. I'm sure this map could have a lot more dots. And if you want to start your own user group, please reach out and we'll help you get started. Another way to get involved are the special interest groups, or SIGs. SIGs exist to help you build areas of TensorFlow that you care most about. We'll have 14 SIGs, with a SIG for TensorFlow JS and Recommenders being the latest additions starting at the end of this month. Most SIGs are led by members of the open source community, such as our fantastic Google Developer Experts, or GDEs. We love our 156 GDEs. They give tech talks, organize workshops, and dog sprints, and so much more. In response to the reinvigorated racial justice movement, we've also created specific initiatives to support the Black AI community. We're funding faculty and sharing content bundles to historically Black colleges and universities, or HBCUs, including having office hours with members of the TensorFlow team. We're also providing donations to Black in AI and AI in Africa groups, as well as offering certificate stipends and course credits to these groups. Speaking of the certificate program, we launched this at the Dev Summit in March, and we've had over 1,000 people spanning 53 countries pass the exam, so congratulations to all of you. This exam was created by the TensorFlow team, and it covers topics such as text classification using natural language processing to build things like spam filters, or computer vision using convolutional neural networks to do image recognition and classification, as well as doing prediction based on sequences. By passing this foundational certificate, you'll be able to share your expertise with the world and display your certificate badge on LinkedIn, GitHub, or the TensorFlow Certificate Network. And to widen access to people of diverse backgrounds and experiences, we're excited to offer a limited number of stipends to help cover the certificate costs. In February, we published a public request for proposals, or RFP, to support professors interested in teaching TensorFlow at their university with a diversity and an outreach focus. We funded a variety of top universities, a mix of smaller colleges, and many HBCUs. Our next steps will be to work with these professors to help them launch their courses. In particular, check out this new open access TinyML MOOC from Harvard on their edX platform, and you can learn more about it on our blog. We know that implementing machine learning solutions can be key to innovating many different types of businesses. However, not all companies have the knowledge, experience, or resources to get started, which is where we hope our TensorFlow AI services partners can help. Our partners are system integrators who are experienced in providing machine learning solutions to their clients. We believe partnering with top AI service companies will help accelerate how machine learning can impact important business problems everywhere. You can learn more about this on our website. 5 years ago, in 2015, we open sourced TensorFlow. It started as a core library for researchers to build and train novel models, and we didn't really know how far it was going to go, but all of you have helped shape where we are today. For example, there are things like models that used to take weeks to train that you can now do in minutes. And today, we're so excited to see the role TensorFlow and all of you are having in the world. I'm looking forward to a brighter future. Thank you so much.
Hey everyone, how's it going? I hope you're doing okay. And this is a talk on a few new features in TensorFlow 2 that I hope will be helpful to you in your projects. So let's take a look at what we're going to cover. And we will dive in by talking about one of my favorite features in a long time, and this is Keras preprocessing layers. And as a TLDR, what they enable you to do is embed the preprocessing logic for text or images or structured data inside your model. And that might sound a little bit strange at first, but I'll show you an example of what this does and why it's so powerful. And the next thing we're going to do is we're going to take a look at tf.experimental.numpy. And the TLDR of this is that it's a partial implementation of the NumPy API in TensorFlow. And this lets you do a couple really important things. The first is that you can differentiate through NumPy code. So, if you're writing a model and you'd like to use familiar NumPy syntax to define your custom layers, you can do that exactly as you would in regular NumPy, and your code will work. And the other thing you can do with this that's really valuable is if you're doing something like scientific computing and you have an existing box of code written in NumPy, as I'm sure many of you do, this is a relatively straightforward way to run your code on a GPU, hopefully without changes. And you can also do fancy things like compile your code with TF function, and you can vectorize it in new and exciting ways to get higher performance. So a new and very cool feature. And next we'll take a look at TF Recommenders. And of course the TLDR is this is a library for writing recommendation engines in TensorFlow. Then we'll take a look at some improvements in TF data, service and snapshot. Service is a way for advanced users to horizontally distribute your data loading and preprocessing code, and this is something you would use if you're running a fancy experiment on a TPU. And we'll look at snapshot, and this is a friend of cache, and it's a way to avoid repeatedly doing redundant preprocessing. And then to close, we'll take a look briefly at two really cool things. One is TensorFlow Privacy, and this is a library for doing differential privacy with TensorFlow. It's very valuable. And then I'll briefly just show you a couple really beautiful results from a paper on a neural radiance fields and just point you to where you can learn more about that. Anyway, let's proceed. So, Keras preprocessing layers. And the tagline here is that you can build models that are truly end-to-end. And as an example, I just want you to take a look at this slide of very limited code. And if you've been using Keras or tf.Keras for a long time, this should probably surprise you, right? So we've got some examples, we've got some strings, and what we're doing is model.predict. But we're calling predict on a batch of strings. And if you're familiar with NLP, this shouldn't work, right? So in order to feed a string through a model, regardless of whether you're doing text classification or text generation or translation or whatever, first you need to vectorize the string. And that's a fancy way of saying that neural networks, they take numbers as input, of course, right? Strings are characters. And so typical NLP preprocessing tasks are you take a string and you standardize it, which is a fancy way of saying you convert it to lowercase and maybe strip punctuation. You tokenize it. So you split, you split a string of, text into a list of words where each word is the token. So the tokens here are the movie was great. And then you vectorize it, which basically means converting words to numbers. And you can do that with a lookup table. So maybe the is 1, movie is 2, and so on and so forth. Or, you can do your lookup in smarter ways too. So, you can calculate all the vocabulary in your data set and you can sort it descending by frequency. So maybe the is the most common word in your data set, so the would be 1. Maybe it is the next most common word, so it would be 2, and so on and so forth. But anyway, you need to do all those tasks before you can feed the text to the model. But with Keras preprocessing layers, all of that code for preprocessing is embedded inside the model itself. So this is important for a couple reasons. And the first thing is that it can make your life a lot easier when you're deploying models. So imagine this scenario, right? Probably like me, you're developing your models in Python. And so maybe I've got a bunch of code to preprocess my text and I've got some code to train the model. But let's say eventually I would like to deploy this model to TensorFlow JS. So I want to run my model in a web page. Now the challenge is that I'm going to have to rewrite all of my preprocessing code in JavaScript, which is not something I want to do because A, there's a lot of it, and B, that's very error prone. If the preprocessing code is embedded inside my model, then it will just work when I deploy it in JavaScript. And all I'll have to do is write JavaScript code to just pass the model strings. So this is a very big deal, and I'm very excited by it. And it works today in Python, and we're just finishing up the JavaScript side of this story now. Before I show you what the code looks like, we spent a lot of time over the summer updating a bunch of the tutorials on the website. And so here are 3 that I'd recommend. We've got examples for you, and there's more too, but here's a good place to start. We've got examples on using these preprocessing layers for images, for text, and for structured data. And I also want to mention the structured data example is fairly important. So, when you're learning about deep learning, there's a lot of excitement with images and text. But the truth is most business problems and most of what you're going to be doing in industry, if you go that route, involve large quantities of structured data. And that's a fancy word for saying tabular data, CSV files, stuff you get out of a database, whatever. So it's very important to have support for that, and we do. And there's also a really excellent guide. And by the way, if you're wondering what the difference is between a tutorial and a tutorial is basically synonymous with an example. So a tutorial is an end-to-end code example. And a guide is basically a book chapter. And so we have both for you. Here's what these layers look like. So this is one of my favorites. It's called the text vectorization layer. And this is great for NLP, obviously. And it does all of those pre-processing tasks that I babbled about a few slides back. So this does tokenization, standardization, and vectorization. And what's really cool about it, if you check out the API doc, it's really nicely designed. And there's a lot of thought that went into this. And it has all sorts of options that might be useful to you. It can pad text, it can trim text, it can produce you a bag of words representation or a TF-IDF, or it can vectorize it as we're doing here with ints. Anyway, there's one step after you make this layer, and what you need to do is adapt it to your vocabulary. And what that means, adapt here can be synonymous with initialize. So this thing is converting words to numbers, so it needs to know what the words are in your training set. And the way you do that is you call adapt with your training data, And, whenever we have these little slides that show snippets of code, obviously it's hard to show you all the steps on just this tiny little screen. But if you check out the text tutorial that I linked to a few slides back, that will give you a complete example for how this all works. Anyway, you adapt it so it can learn the vocabulary. And then here's what's new. When you define your model, and of course this works with models that aren't just sequential, you can do this with the functional and subclassing models if you like as well. This is a layer that you can put inside your model just like any other. And so the preprocessing will happen when this model receives text. It's super cool. And of course, and we show this in the example too, you can also use this layer outside of your model. So if you'd like to do preprocessing there, you can do that as well. This is the cool thing. When you save your model, this layer is saved along with your model just like everything else. And so anyway, really great idea, really big deal. Optional to use. If you don't want to do the preprocessing inside your model, you don't have to, but it's really valuable, and there's a couple different things you can learn about. Now let's take a look at experimental.numpy, and I think you're really going to like this. And in a nutshell, let me tell you, A, how to learn about this, and B, how to use it with, like a one-line, easiest possible way to get started. The way to learn about it is you want to visit this website, and we just published a new guide, aka book chapter, which I hope will be helpful. But here's the basic idea. Typically, when you import NumPy in your program, you would write import NumPy as NP. If you want to use TensorFlow.numpy, you write import TensorFlow.numpy as NP. And you notice that we're importing both libraries as the same thing, and most of the syntax will be the same between them. And that means you can run your existing code on the GPU and do other fancy things with it, like this. So you can differentiate or backprop through your code. This means you can use NumPy code to define your layers or to define custom training loops or other places in your model. And of course, you can run it on the GPU and TPU. And I don't really want to read these slides to you, but the TLDR is that it works with the rest of the TensorFlow stack. And so I have a couple slides here that were actually made by a friend of mine at work. And I just wanted to quickly show you at a high level what this can do. And you can check out the guide that I pointed to learn more. So now let me walk you through at a high level how this works. And this is just a quick slide of code. And what we're doing is we're importing the library and we're creating some random data. And here we're showing you that if you check the device that this operation is running on, you'll see it's running on the GPU. Great. So we're just showing you that TensorFlow NumPy works on the GPU. That's cool. But here's the more important part. When you're creating data with tf.numpy, the data that you're making is a TensorFlow tensor. That means it can run on GPUs and TPUs. But it also implements the array interface defined by NumPy. And importantly, that means you can import other libraries, like one of my favorites, matplotlib, and you can pass your TensorFlow NumPy objects to matplotlib. And even though matplotlib expects a regular NumPy object, it will just work because it defines the same interface. And so we have compatibility with existing libraries, so you shouldn't have any headaches there. And that's important. You're probably interested in performance, and I have good news with caveats. So if you've properly configured your TF NumPy code and you're working with large amounts of data, it can be order of 5 to 10 times faster than regular NumPy, which is a really big deal. But you should know, and you can read more about this on the guide, if you're working with a very small amount of data, TensorFlow is a larger library than NumPy. It has some overhead. So with tiny amounts of data, it might actually be slower. And so you should think about whether the performance benefits on GPUs are going to make sense for your use case. And also, there's a couple tricks that I'll show you in the next couple slides that you can use to accelerate your code. And what this is before we get into that, this is just another quick code example of using TensorFlow NumPy. And we're just going to show you that you can differentiate with it just like you can any other TensorFlow code. So here we're making some data. And we have, if you've ever written a custom training loop in TensorFlow, or you've ever done, you needed to calculate gradients from scratch, like say you were doing something like Deep Dream, or you were doing something mathy, this is how you use the gradient tape. So we're writing a function to compute gradients. And what we're doing is we have a for loop here that feeds our data through our gradients function and computes the gradients for each batch. And there's a lot of code here, but the basic idea is that NumPy works with TensorFlow. TF NumPy works with TensorFlow just like any other TensorFlow code. What we're showing you here is that instead of writing something like a sigmoid from scratch with NumPy, you can also freely use the existing mathy TensorFlow functions, which are probably more numerically stable. And this slide is also showing you, just as a neat thing, if instead of computing the gradients for the batch, you would like to compute gradients for each individual example, this is a way you can do that. And then there's one more cool thing, and this is advanced, but this is showing you how you can compute gradients per example in a very fast way. And here there's two things that are important. One is TF function, and roughly you can think of that as trace compiling your code. And two is TF vectorized map. And so you're computing gradients for each example in parallel. And I know there's, I joke about my eyesight a lot. If you have better eyesight than me, or you read the guide, you can check out that tiny little performance graph. And the TLDR is that if you need to go fast and you're willing to write a little bit of advanced code, you can definitely do so with tf.numpy. But again, performance benefits will vary by your use case. Anyway, we're really excited about this. There are a couple caveats of things that might be gotchas. The first is that if you have a regular NumPy array, you can do in-place mutation. We can't do that yet with TensorFlow NumPy, but we're thinking about it. And then the team is working on the things that you see here. Anyway, so far, super cool project. I'm very happy with it. Okay, the next thing we'll talk about is TensorFlow Recommenders, and I'll just give you a couple quick slides and high-level overview of what this is. So, unsurprisingly, you can use TensorFlow Recommenders to develop recommendation systems with TensorFlow. And all I really wanted to say here is that if you're new to recommendation engines, there are two terms you're going to see on the website. You're going to see things called nomination models or retrieval models and ranking models. And the basic idea is this. Let's say you're developing a recommendation engine. You know, maybe I go onto Google Play or Google TV or whatever, and I search for like a science fiction movie. I search for like Star Wars. Google Play has, you know, whatever, like a million different movies it can recommend to me. And the challenge is that, you know, if you use a very complicated recommendation system to carefully analyze, like, is Josh going to like each one of these million movies, that can be quite slow. So often one strategy will be to use a first model called a retrieval model. And what that will do is, you know, very quickly with lightweight code, narrow down those million movies to maybe something like 1,000 reasonable possibilities. Then you'll have a second model, which is a little bit heavier or more fine-grained, called a ranking model. And what that will do is it will rank, or, you know, maybe sort those descending by the probability that I'll actually like to watch them. So you've got these two different types of models, and they're friends and they work together. Anyway, there's also lots of advantages of course, TensorFlow Recommenders. It's a system for building, you know, deep learning-based recommendation models, and there's many advantages of these over traditional things that you would do that might be a little bit more mathy, like matrix factorization. So I personally like the deep learning models just because it's easier for me to think about, because I come from a software engineering background, not a math background, although of course there's a lot of overlap. But also when you have a deep learning based model, it's easy to feed in rich features. So for example, you know, maybe you have a lot of data about the movies and you have a lot of data about the users. And for example, let's back up for one sec. This is an example of what a common type of, you know, deep learning based recommendation model might be. And here you see two towers, and you can think of each of these towers as, you know, you can write this so it's one large neural network with a bunch of inputs, or you can actually write these as two separate neural networks that are jointly trained and cooperating with each other. But you have a query tower and a candidate tower. And roughly, you can think of the query tower as maybe taking features about the user. So, you know, I'm Josh, you know, this is my age, you know, maybe I'm based in New York or Philly or whatever. These are the movies that I've liked in the past, and this is what I'm searching for. And you have the candidate tower that could take features about a movie. And you can think of this neural network as making a prediction, will this user like this movie? Here's why it's cool to do this with a deep learning setup. Let's say you have rich features about the movie. You might have structured data like, you know, how many stars did some reviewer give the movie? You know, when was it made? How many million views does it have? But you also might have rich data, like a plain text description of the movie, or the plain text description of a review, or even if you want to get super fancy, even like a picture of the box. When you have a deep learning based model, it's possible to feed in that rich data. And this is an area of research, but the point is with a deep learning model, it's natural to feed in this rich data if you would like to. And that's challenging to do with other approaches. But the best place to go to learn about TensorFlow Recommenders is tf.org/recommenders. Okay, so now let's take a look at two new features in tf.data. And before we even talk about those two features, I want to talk about why I like tf.data. And I will admit that it does take a little bit of energy to learn, but there's a very good reason for you to actually invest the time to get it right. And the TLDR is that the most common performance bottleneck in most deep learning programs that I see is the input pipeline. And what this means is that you'll have a developer with a very fast machine, maybe an expensive GPU, or maybe they're doing cloud computing and they've got some fancy thing on the cloud, or maybe they're even doing distributed training and they've got multiple GPUs. The thing you want to avoid is called GPU starvation, which basically is a slightly weird way of saying that your GPU is sitting idle waiting for data. So the challenge is that your CPU can't load data off disk and preprocess it and get it to the GPU fast enough. And the way you fix this is by using some of the really, really powerful features in TF data. And roughly what this slide is showing is that GPUs have gotten faster than CPUs. The other reason this happens a lot is a lot of developers, if you're like me, you took a machine learning class and maybe it had a ton of math, or maybe you used scikit-learn, or maybe you worked with toy data sets that fit into memory. And so just for whatever reason, a lot of us just don't have the mindset, and we forget that loading data off disk is super slow. Before I get into the new features, here's the easiest possible thing you can do to make your code run much faster. And TF data has two really awesome features. We've updated a ton of tutorials to use this. If you search through the tutorials, look for the section that says configure your dataset for performance. And there should be copy-pastable code. It's one line that you can use in your programs to go faster as well. What they are is they're prefetch and cache. And prefetch lets the data loading and preprocessing code run on the CPU while your GPU is classifying data, so they can run in parallel. Cache can do two things. It's amazing. Cache can automatically, if your data set will fit into memory, cache can keep it in memory for you after it's loaded off disk. So of course you have to load it just once. And what this means is when you're training a model, the first epoch will be slower because it's loading the data. Subsequent epochs will be super fast because it's in memory. Importantly, if your data set doesn't fit into memory, cache can also automatically create a high-performance on-disk file cache that's much faster to read. So for various reasons, if you've got tons of tiny files like text files or JPEGs, it can be faster to read on different systems one large file instead of a lot of small files. And cache can help you solve that problem automatically. You just call dataset.cache and you give it a file name, and it will take care of the rest. There's also two really solid guides you should check out. People spend a lot of time on these. They're very well written. One is the data performance guide, and that's like a book chapter. It's basically, there's a lot of background knowledge. It's great. And another is using the TF profiler that I'll talk about in a sec. Anyway, that's the existing stuff. And then quickly, here's two valuable features in TF2.3. One is dataset.snapshot, and this is a more advanced version of cache. And basically, cache is intended as a one-time use kind of thing. Snapshot is very similar. It can cache your data to disk, but it's designed to read it back in a more high-performance way. And this is something you would use. Let's say you're doing a research experiment or you're doing hyperparameter tuning, and you have a lot of expensive preprocessing that you're going to need to run many, many times. With Snapshot, you could run that preprocessing once and then cache or save the results to disk. And then subsequent runs of your pipeline can very quickly load back all that expensive preprocessing and just get on with the experiment. And then TF Data Service, this is a feature for power users. And so let's say you're training a fancy model on a TPU, and your accelerator is so fast that there's just no way to load the data off disk quickly enough. Service lets you horizontally scale your data loading, so you can have multiple machines reading data in parallel and pre-processing it in parallel, and then sending it back so you can train a model or whatever. So that's also extremely cool. This is just a diagram of what Snapshot is doing. Basically, it takes your data set in. If you've already done some computation, it's going to read it from disk. If you haven't, it's going to do the work and write it to disk. And it's super cool. What's nice is here's how you use Snapshot. And if you take a look at this slide, this particular slide happens to be loading data in TF record format. I just wanted to mention, if you're using TF records, great, they're very fast. If you're not, you do not have to. This is completely optional. Behind the scenes, Snapshot is going to write your data in a high performance format anyway that you don't need to worry about. So it's totally valid to just read in JPEGs or read in text files or CSVs or whatever you want, and you don't need to worry about converting it to TF records yourself first. And also over the summer, we spent some time updating the load data tutorials on TensorFlow.org, and we've got more modern versions of a few of those you can check out. Anyway, here's how you use snapshot. By the way, you can also see prefetch on this slide that I mentioned earlier. So you have an existing pipeline, and the way to use snapshot, it's one line of code. And the thing to remember is that anything before your snapshot operation is going to get saved to disk, and anything after it is not. And importantly, snapshot freezes the data, and oftentimes you need to shuffle your data, and it's basically just important to do the shuffle after the snapshot if you want, a different order of your training examples every time. And then here's a high-level diagram on how tf.data service works. And like I said earlier, basically, you're setting up a cluster of machines to do the data loading and pre-processing. What's really nice about service is after you've set up the cluster, which of course is going to take some work, it's relatively easy to use the service itself. And so again, you don't need to be using these records unless you'd like to, which is totally cool. But once you have a pipeline, you can distribute it with the distribute transform. And this is super cool. So anyway, I think the team did a really nice job on this. I'm personally not doing any, super scale experiments. I'm focused mostly on how can we write code clearly. But I think for people who are, I hope this will help you make your code run even faster. And there's a lot of API doc that's been written already in the dispatcher and the worker that's linked here. And there's also a complete example, and you can check out how to use this on Kubernetes. Right, so here's a summary of the things we talked about earlier. I would basically just say this. If you are using one machine, or even one machine with multiple GPUs, or even multiple machines with multiple GPUs, the easiest possible thing, which you should not forget to do to make your code faster, is use prefetch and cache. If you're running experiments and you want to use basically the same cache code many times, snapshot is your new friend. It looks super cool. And if you're an advanced user and you need to do, parallel data processing, check out tf.data.service. And this is why it's worth your energy to learn tf.data, because writing all these things from scratch in Python would be a mess. And lastly, here's a couple guides you might want to check out. Okay, let's take a look at the TF profiler. And I know I've been talking a lot about optimizing your data input pipeline. And not coincidentally, there's a really awesome feature in the TF profiler that you can use to analyze your pipeline. And roughly what we're looking at here, if you look at this chart, this is showing you how much time is spent loading data off disk, which you can see in the red here, compared to how much time is spent actually classifying the data on the GPU, which you can see in the purple. And what this tells us when you see a chart like this is it's telling you your program is highly input bound. And this is what you want to avoid. And what's really, really awesome about this feature in the profiler, if you have sharp eyesight, you can see there's recommendations for next steps. And what this is basically going to say, it's going to say, hey, go read the data performance guide. You might want to check out cache and prefetch. And you can use this to make sure your code is running fast. There's other really awesome tools in the TensorFlow profiler. One is the memory profiler tool. And in a nutshell, this can show you, which operations are consuming the most memory over time. You can also use this, if you're an advanced user, you can check out memory fragmentation. And there's other things it can do to help optimize your code. You can learn more about it on the website. And then another new feature, which is really powerful, is the Python tracer. I know there's a lot happening on this slide. You can read more about it on the website. But roughly, what this can be useful is you can also see which parts of your program are executing on the CPU versus which parts of your program are executing on the GPU. And you can also use this to tune the performance of your models. And to learn more about the TensorFlow profiler, there's this really nice guide on the website you might want to check out. Okay, so in a nutshell, those were a few of the new features. And after talking about these, I want to point you to two really cool things that are more on the research slide that I think are really fun and interesting to think about. And the first is very important. It's called TensorFlow Privacy. And in a nutshell, this is a library to do differential privacy with TensorFlow. And then I just want to show you one picture from a really beautiful paper. Okay, so let's think about what it means to do privacy in the context of machine learning. And in a nutshell, it means this. If you're training a model, let's say on user data, and you have many thousands of users, what you want to make sure is that the model is not memorizing the details of any single user. And let's say you're actually sharing the model. Maybe you have an open source project, you train a model, and you save it, and you upload it to GitHub. You want to make sure that any individual's data is not recoverable from that model, right? So it doesn't memorize any single person. It just learns general characteristics. And that's what we mean when we say differential privacy. And here's some cool slides just to illustrate this idea in a nutshell that I borrowed from a friend of mine. And here we're looking at an image of the Mona Lisa. And of course, images are made up of pixels, but here let's think about this very abstractly. And the Mona Lisa is some general pattern that we want to learn from the data. And the idea is that instead of pixels, we're going to imagine that each little pixel here is actually a data point. Maybe it represents some user in the training set. And what we want to make sure is that when we share the picture of the Mona Lisa, no one can zoom in and recover data on individual users. And one way to help with this is you can randomly add noise to different training examples. So here we might flip an M to a period or vice versa with some probability. So the important point is that although we're adding noise to individual training examples, when you zoom out again, the overall pattern is still apparent. And this means that if you have enough data and you're adding noise, the model can still learn general features, but it's going to have more trouble memorizing individual details. And there's a lot of math behind this that you can read about on the website. But the basic idea is that using TensorFlow privacy, you can quantify the chance that a model has memorized an individual piece of training data. And that's very valuable. It's a new and active area of research. I think it's super cool and super important. And if you're interested in this, you can check it out. And in closing, I just wanted to point you to a really cool paper called Neural Radiance Fields. And this is solving a really fascinating problem on 3D landmark reconstruction. And the basic idea is this, and I apologize to anyone who speaks German, I'm surely going to mispronounce this, but we're looking at a 3D reconstruction of the Brandenburg Gate in Berlin. That video you're looking at on the right is something that was the output of a model, and it was produced by a noisy collection of images, meaning we're inputting to the model thousands of images of this gate, but they were all taken at different angles, in different lighting conditions. Some of the images had people or cars in front. So it's a noisy collection of photographs. And from that, they've developed a technique to reconstruct the original model and allow you to explore it in 3D. So this is, it's really gorgeous. And another thing they did too is they enabled, their software can also dynamically value both position, so the angle with which you're viewing the landmark, and also things like the time of day. And it's just a really awesome piece of work in machine learning-based computer graphics. And it's too much for the 30 seconds that I have at the end of this talk, but I wanted to point you to their website paper, and they have a YouTube video that also explains the core ideas. So if you're interested in this type of work, this was definitely a wow moment, I think, for computer graphics, and you might want to check it out for fun. So thanks very much. The best way to learn about the most recent features in TensorFlow is tensorflow.org/tutorials. That has our best collection of end-to-end examples. We also have a really solid guide that has a ton of book chapters that I hope will be helpful. And of course, we have a blog, a YouTube channel, and Twitter. So thanks very much, everyone, and I hope you find all these new features useful.